In this video, we're going to cover the topic of isotopes. So in the previous video, we looked at atomic symbols, and we looked at how we can sort of identify the number of protons, neutrons, and electrons in a particular atom. So in this video, we're going to look at what happens when we start to change the ratio of some of those different subatomic particles. One of the ways that we can change the ratio of subatomic particle is to change the ratio of protons to electrons. This leads to what we call a charge. In this video, we're going to talk about what happens when we start to change the ratio of protons and neutrons. And this is what leads to isotopes. So an isotope is by definition atoms of the same element. And so right here we can kind of put in parentheses, so we're talking about the same number of protons but differ in the number of neutrons. And so really what we have is we have the same element but with different mass. Different mass numbers. So let's take a look at an example. So one example is hydrogen. And we're just going to spend a couple of seconds talking about hydrogen. Hydrogen comes in a couple of different flavors. You have hydrogen 1, you have hydrogen 2, and you have hydrogen 3. That's called regular hydrogen, then there's deuterium, and then there's tritium. And then there are many other isotopes that you can have of hydrogen. So what we're changing is we're changing the number of neutrons. So let's look at an example. Hydrogen is one example, but let's look at an example where we can kind of get into it kind of simply, which is chlorine. So there are a couple of things that we should talk about as we start to introduce this topic. So there are two different types of isotopes. We have stable, and we sort of have this other one called unstable. So a stable isotope is exactly that, meaning in nature you can have this isotope and it'll last for an extended period of time. Even some unstable isotopes will have half-lives of millions of years, so they'll be around for very, very long periods of time. But a stable isotope is an isotope that can exist and it doesn't have any kind of radioactive breakdown or decay. Whereas an unstable isotope, even if it takes a very long time, it will inevitably break down into something else. So when we look at elements in nature, elements in nature are composed of a mixture of stable and unstable isotopes. But generally, what we look at is, so for the example of chlorine, in chlorine, all of the chlorine isotopes, for the most part, are stable, and then the unstable ones are only generated by some kind of unusual radioactive event. So with chlorine, we have two stable isotopes, and we're going to look at those in a second. But there are other atoms, like uranium, that have stable isotopes, and they have unstable isotopes, and that kind of comprises the natural sample. So this is just sort of an introduction. We're not actually going to talk about this in too much detail, because we get into this more when we get to radioactive decay in the second semester. But you should have an idea that there are some isotopes that are stable, some isotopes that are unstable, and in nature, the elements are composed of a mixture of these isotopes, and if the isotope is unstable, over time, that mixture will change. So that kind of gives you a brief. Now let's actually look at two examples of isotopes. So with chlorine, we have two types. So we're going to write the symbols. We have 35 chlorine, and you'll notice that I wrote the proper symbol here. So we have the chlorine, the Cl indicates that it's the element chlorine. I put the 17, which is the atomic number, and the 35, which is the mass number. And then we have what we call 3717 chlorine. So another way of writing this could be written as what we call Cl-35, and Cl-37. That's another way of indicating this. Or you can have the full name chlorine 35 and chlorine 37. Those are all different ways of representing the fact that these are different isotopes. So you'll notice, let's just kind of sort of start to think about this in terms of the number of protons and neutrons. So if we want to do the number of protons and we want to do the number of neutrons, we'll start with the simplest one. So both have 17 protons, meaning they're the same element. And then they're going to vary by different numbers of neutrons. So in the case of the 37, there's a difference here of 20. So we have 20 neutrons. And in this case, there's a difference of 18 in the proton and neutron number. So when you add 17 and 18, you get 35. When you add 17 and 20, you get 37. So you can see that these are both the same element because they have the same number of protons, but they vary in the number of neutrons. So that introduces the topic. And when you look at a sample of chlorine gas, you're going to get a mixture of these two things. And we can actually look at the percentage. So there's what we call the fractional abundance. And the fractional abundance in this case is 75.77% chlorine 35 and 24.23% chlorine 37. So to give you to put a definition for the fractional abundance is the percentage of each isotope in a natural sample of an element. Now there's an interesting thing that we can do with isotopes. So if chlorine is composed of different percentages of 35 and 37, we can start to think about this. So we have Cl35, and if this is at 75.77%, that's our fractional abundance. And we have 37 Cl, and this is at 24.23% of our fractional abundance. So let's think about if we were to just take a sample of chlorine. What would the mass be? So if we were to kind of just average out the mass of these two things, it's not going to be 35 because it's not 100% 35, and it's not going to be 100% 30. It's not 100% 37, so it's not going to be 37. So the mass is going to have to be somewhere between 35 and 37. And we can actually calculate it exactly. And so if you think about it, if it's 75.77% 35 and 24.23% 37, the mass is going to be somewhere between 35 and 37, but it's going to lie somewhere closer to 35, right? Because it's mostly 35. So we would expect something like 35.5, 35.6. Is there a way, though, that we can calculate the mass of a natural sample? So let's do that. So there's a way of calculating this, and it's just like you would do this if you were calculating a proportion for your grade. Like let's say that your grade was made up of 20% experiments, 20% quizzes, 20% tests, 20% homework, and 20% participation. You got 5 things, each one weighs 20%. Well, what you would do is you would take your grade for each of those, multiply it by 0.2, and then add it up, and then that's going to give you your overall grade, and it's going to be based on the weighting. Well, we can do the same thing. So to figure out the average atomic mass, this is going to equal the fractional abundance of an isotope multiplied by the isotopic mass, and then we're going to add that up for all the different isotopes. So this is going to be the fractional abundance of 37 times the isotope mass for 37, and then there's going to be the fractional abundance for 35 times the isotopic mass for 35. And so let's actually calculate this out and see if we can get an exact number. So the fractional abundance for 37 is 0.2423. Now you'll notice that I converted the percent to a fraction. The reason for that is because in this case we have to use the fraction because we want to multiply it. When we multiply it out, the fraction will allow us to do the weighting, and then we multiply this by the mass. And then we're going to multiply this by 37 AMUs. Now, for the purpose of this lecture, the 37 AMUs is a bit of an approximation. Each isotope has a much more accurate mass than just 37. It's going to be 37 point and then have several decimals after it, or it could be 36.9 and several decimals after it. But for the sake of just this discussion, we're going to just do a very simple, rough calculation, and it's going to give us a very good estimate anyway. But when you get this on the exam, you're going to get an actual mass that's going to be much more precise. So for the sake of this lecture, we're just going to kind of use the overall 37 and the overall 35 for clarity purposes. So now we've got the weighting for the 37, and then we can add to this the 0.7577 times the 35 AMU mass. And when you do this, when you multiply 0.2423 times 37, and then you add 0.7577 times 35, the fractional abundance you get is about 35.45 AMUs. So that's our average atomic mass. And this is actually very important, the average atomic mass. If you go to the periodic table and you look at chlorine, the mass that's listed for chlorine is, I got my periodic table right here. Let's take a look and get that mass, is 35.453. On the periodic table. So what's listed on the periodic table is what we call the average atomic mass. So the atomic weight on the periodic table is this is the average mass of, it's the average weighted mass of all the naturally occurring isotopes of an element. So when you look on the periodic table, the mass that's there is not going to be the mass of any one particular isotope. It's going to be the average mass of all the isotopes. So now let's talk about what the AMU is. So we've introduced this unit of AMU, and it's time now that we explore where this comes from. So in general, the mass of an atom is about 10 to the minus 24 to 10 to the minus 23 grams. These are incredibly small masses, and we use the AMU to sort of summarize these masses so that we can have like round numbers, right? Because if we were dealing with times 10 to the minus 24, it makes it harder to work through things mathematically. So how do we come up with the AMU? So we call this the relative atomic mass. And by relative atomic mass, in essence, what we're doing is we're setting the scale for the AMU. So where does that AMU come from? And what it is it's basically they decided that the AMU would be based off of the carbon-12 isotope. So in the carbon-12 isotope, you have 6 protons plus 6 neutrons gives you a total of what they called 12 AMUs. So they accurately measured out the mass of the carbon-12 isotope. And what they did was, so they said, so the mass of a carbon-12 isotope, and they took that and they divided it by 12. So they said, if this thing is made up of 6 protons and 6 neutrons, for a total of 12 subatomic particles that have mass, we'll divide that by 12 to figure out what the mass of one would be. And that's equal to the mass of 1 AMU. So the mass of 1 AMU is equal to the mass of a carbon-12 atom divided by 12. And then that gives you the mass of 1 AMU. So 1 AMU, based on this scale, weighs 1.66056 times 10 to the minus 24 grams. So a hydrogen-1 atom, the hydrogen-1 isotope, is going to have a mass of 1 AMU. It has 1 proton. And so that is going to weigh 1.66056 times 10 to the minus 24 grams. Now, the reason why we define AMU is because then it becomes much easier to understand. So instead of saying, well, okay, the mass of a hydrogen-1 atom is 1 AMUs, and if we have the hydrogen-2 atom or isotope, this is going to be 2 AMUs. So hydrogen 1 is just 1 proton, and hydrogen 2 is 1 proton plus 1 neutron. So they're isotopes of each other. They vary by the mass of a neutron. And you can see this makes it much easier to see. For this case, we have 1 AMU. For this case, we have 2 AMUs. We can see that it varies by 1 neutron, instead of these sort of odd numbers that are much harder to take ratios of. So it's going to turn out that when we learn about moles, it's going to turn out that 1 AMU is going to be the same thing, is going to be equivalent to 1 gram per mole. So, for example, many of you are probably familiar with this, that the mass of carbon, when you use this for stoichiometry, is 12 grams. If you look at the periodic table, many of you would say, and you looked at the periodic table to do stoichiometry, if you wanted to figure out the number of moles of carbon you have, the 12.011 would be what you would use in your stoichiometry equation. Well, the reason for this, and we're going to show this later on, is that 1 AMU is proportional to 1 gram per mole, and that's because the AMU can be scaled using Avogadro's number. So that's going to come in chapter 3. Okay, so in this lecture problem, we're going to look at going in the reverse direction. What we're going to do is we're going to get an average atomic mass, and we're going to be asked to come up with the fractional abundances for 2 different isotopes that are built in. So in the previous problem, we were given those fractional isotopes and asked to go and get the average atomic mass. In this case, we're going to be challenged to go in the reverse direction, from the average atomic mass back to the fractional abundances. So if we read the problem, it says, boron has 2 naturally occurring isotopes, boron 10 and boron 11. If you look on the periodic table, an average mass of boron containing both isotopes has a mass of 10.81 AMUs. What is the abundance of each isotope of boron? So we basically have boron 10 and boron 11. So if we write those down, and if you go to the periodic table, so for boron 10, you can find out that the number of protons from the atomic number is 5. So our 2 isotopes are boron 10 and boron 11. So they vary by 1 neutron. This one has 5 neutrons, boron 10, and boron 11 has 6 neutrons. And each one of these are going to have a fractional abundance, which we don't know what they are. But we know that the average mass, we know that the average mass is equal to 10.81 AMUs. So just looking at that average mass, we can see that if there's boron 10 and boron 11, if it were 100% boron 10, the mass would be 10. If it were 100% boron 11, the mass would be 11. So in this case, we're somewhere in the middle, and we are much closer to the 10. We're much closer to 11, because we're past 10.5, than we are to 10. So this sample is going to have more boron 11 in it than it's going to have boron 10. And I could just tell that by looking at this number, because if you think about it, if it were 50-50, it would be halfway between boron 10 and boron 11. So we're past the 50-50 mark, so we're going to be at we're going to be much closer. We're going to have much more boron 11 than we are going to have boron 10. So that's one way to kind of look at it right away. You can kind of just get a sense and sort of situate yourself by looking at the 2 isotopes that are present and what the mass is and where it falls between the 2 masses of those isotopes. So if we want to do this quantitatively, though, we have to write out our equation. So we have the fractional abundance of 11 times the isotopic mass of 11, plus we have the fractional abundance of 10 times the isotopic mass of 10, and this is going to all equal 10.81 AMUs, which is the average atomic mass. So if we plug in, we can delete these guys. If we plug in for the masses, so we know from up here that we have one with a mass of 10 and one with a mass of 11, that this guy is going to be 11 AMUs for the 11 AMU isotope, and this one's going to be 10 AMUs for the 10 AMU isotope. So we're basically setting this up. Now our job is to solve this equation to try to figure out what the fractional abundances are. And you're going to notice that we can't do that because we have 2 variables. We can't solve for 2 variables at once. So we have to think a little bit more cleverly about this. One way that we can help ourselves is to understand this hint. It says, keep in mind that the 2 fractional abundances must sum to 100%. So in essence, what we're saying here is no matter how much boron 10 and boron 11 we have, the whole sample can only be made up of 100% of the two, right? So if we have 50% boron, then we have to have boron 10, then we have to have 50% boron 11, right? If we have 40% boron 10, then we have to have 60% boron 11. They're locked into that conservation of mass type situation. So what we can say is, well, the fractional abundance of 10 plus the fractional abundance of 11 has to add up to 1, meaning all of the isotopes have to add up to 100%. So we can actually solve this. In terms of the fractional abundance. And what we're going to do is we're going to use these two simultaneous equations to kind of help ourselves out. In essence, what we can do is we can get rid of one of the variables. And the variable, we can pick either one, but I'm going to pick the fractional abundance of 11 to get rid of that one. So what I can do is I can subtract the fractional abundance of 10 from both sides. And what I get is the fractional abundance of 11 is going to equal 1 minus the fractional abundance of 10. And now what I can do is I can plug this in up here. So I can plug into this equation that the fractional abundance of 11 is 1 minus the fractional abundance of 10. And I plug that in for the fractional abundance of 11 because we solved and we said that this variable is equal to those two variables. So this is going to be times 11 AMUs. And then we get the plus the fractional abundance of 10 times 10 AMUs. And now we have an equation that only has one variable in it. And so this just becomes a simple algebra problem. So the first thing we have to do is we have to do some distributing. So we're going to distribute the 11 AMUs in. So we get 11 AMUs over here. 11 AMUs times 1 is 11 AMU. We're going to get minus 11 AMUs times the fractional abundance of 10 plus the fractional abundance of 10 times 10 AMUs. And that's going to equal 10.81 AMUs. And so now we can combine terms. So we have 11 AMUs times the fractional abundance of 10, and we have 10 AMUs times the fractional abundance of 10. So these are the same set of variables. And when we add these together, we basically have minus 11 plus 10 is going to equal minus 1 AMU times the fractional abundance of 10. Remember, you can always flip-flop this. So see how I have the fractional abundance of 10 times 10 AMUs? We could just simply say that that's 10 AMUs times the fractional abundance of 10. That's just a mathematical rule. So you can always, but they are the same. So it's basically like 11x or x times 10. It's the same thing. Okay, so then we have 11 AMUs minus 10 AMUs times the fractional abundance of 10 is going to equal 10.81 AMUs. So now if we continue with our algebra, we can subtract the 11 AMUs from both sides. And what we're going to get from that subtraction is minus 0.19 AMUs. And then this is going to equal minus 1 AMU times the fractional abundance of 10. And then so if we divide both sides by minus 1 AMU to get the fractional abundance of 10 all by itself, what we're going to get is, so I'm going to continue here. We're going to get that the fractional abundance of 10 is equal to 0.19 because it was we had a minus 0.9. What we had here was that we had minus 1 AMUs times the fractional abundance of 10 is equal to negative 0.19. So when I divide the negative 1 by both sides, I get a positive 0.19. So we now have the fractional abundance of 10, which is equal to 0.19. So this thing is going to be 19% of the boron 10 isotope. And remember, the fractional abundance is the same thing as a percentage. So if we multiply this by 100, we go from the fractional to the percentage. And then we can use our simultaneous equation. We had our simultaneous equation that the fractional abundance of 10 plus the fractional abundance of 11 has got to equal 1. So if we want to get the fractional abundance of 11, we just are going to solve for that. So we plug in 0.19 plus the fractional abundance of 11 is equal to 1. So we get, for the fractional abundance of 11, we get 0.81, or 81% boron 11. The important thing is you have to set up these two simultaneous equations. So this equation allows you to set up all of the information about the masses and the average mass. And then we have this other one, which is the fact that the two fractional abundances must sum to 100%. And then with that, we can get the fractional abundances for the two isotopes. You got to practice this, guys. The most important thing is to make sure that you can actually do these calculations, to set up the algebra. So we'll have some practice problems that relate to this, and there'll be some problems in the homework. But this is really your first test in terms of making sure that you remember your high school math, making sure that you know how to do your algebra, and making sure that you can kind of solve some simultaneous equations. It's not hard, but you just have to make sure that you can do your algebra correctly.